Equation for these two, for this one, and this equation for that one. Nothing wrong with that either. But for solid circular shafts, and only for solid circular shafts, it doesn't apply to anything else. For solid circular shafts, this is equal to, this is the maximum shear stress. (16t divided by pi d cubed). This comes from the fact that J is equal to pi d to the fourth divided by 32, and C is, let me write that here, C is d over 2, J is pi d to the fourth over 32. And then this one turns into 32m divided by pi d cubed. And I equals half of J. This equation is much easier to use, and you need not calculate the moment of inertia. It's strictly in terms of the diameter. And it comes in handy. But make sure that you only use it for solid circular shafts, not hollow. Doesn't apply to hollow. So you do these, and you find these numbers. That tau is equal to the maximum, the shear stress on the outer fibers, 12.22 KSI, and sigma is equal to 14.7 KSI, the maximum tensile stress. So your stress element looks like this. And you are looking at a point such as this. And if you take a look at the picture for that point, the torque coming from the 4-inch diameter gear is along the positive direction of the x-axis. Therefore, you have something like that. Put that one there too. And this was 12.22. Okay. Then you draw more circle and find principal stresses if you want. But in the quiz, that's all you have to do. You have to draw that element and show all of the stresses acting on it. If you wish, you can continue, find the principal stresses, maximum shear stress, their directions, and all of that. Okay. Any questions?
Was the quiz out of 10 or 20?
I'm sorry?
Was the quiz out of 10 points?
10.
20 points?
10.
Okay.
Quiz was out of 10 points. Yeah, it would be bad if the maximum was 10 out of 20. It would not be good. Any other questions? Before we continue with the stuff we were working on last time, let me show you something here. Last time we started the whole thing with a discussion of stress concentration. And I'm going to say a few words on that. Maybe I should have done this last time, but it's not too late. Before the advent of the finite element method, which, anybody here taken finite element? You have, okay. Before the advent of finite element method, which was, or is, a method by which you can get a whole field view of the stresses. By that I mean, if you have a part that's under stress, it will give you a picture of that part with higher stresses in red and then in pink and then in yellow and then in white and all of that. So you can identify points of high stress. And of course, you can also calculate magnitudes of stress. Before that, and even now, this method is used. A method was used called photoelasticity, in which you take advantage of the fact that some materials bend light when they're under stress. So let me briefly go over this, and it is essential that you at least have an idea of what this is. We won't go into any sort of detailed analysis, but you should know what it is just in case you go for a job interview and the guy asks you whether you know anything about photoelasticity or not. You can say yes. It is based on this fact that if you have a polarized lens or glass, such as some of your sunglasses, polarized sunglasses, all that a polarized glass does is to cut the incoming light, white light, let's say, which vibrates in all directions by one of its components. It will pass, depending on the axis of polarization, it will cut one of the components entirely off. So, let's say this is a polarized glass, and let's say the axis is directed like that, axis of polarization. This means that white light that vibrates in all directions crosses this, gets off the other side. The only thing that remains, the part of the white light that is vibrating in the vertical direction. None of the components in the horizontal direction pass through. Therefore, if I put another one of these polarized lenses here, so white light comes, goes through this, one component cuts off. Let's assume the polarizing axis of that is like so. How much light do I get over here? Nothing. That's right. One component cuts off all of the vertical components, the other one cuts off all of the horizontal components, nothing remains. In other words, it'll be black, no light. There are some materials called birefringent. If you put those materials, these materials have the capability of bending the light. In other words, if it is vibrating in this direction, they bend it through some sort of an angle. And they bend it because they're being stressed. The more the stress, the more this bending process. So if I put one of these birefringent models here, now the white light is coming in here, only vertical component, goes through here, gets bent by this, comes out looking like that, for example, in some other direction, or combination of directions. Then when it passes through here, it won't be zero light over here anymore, because this only cuts off the horizontal component, so some of the vertical component remains. We measure that optically, and you can do it analytically as well. And that'll be a function of the stress that's applied to this material. If no stress is applied to it, it doesn't do anything. You still get black over here, no light. So let me show you. Here I have, and for this, would you please hit that light for just a few minutes? Okay. These are two polarized lenses. Now you do see some light coming through them because there's only one of them. They do have their axes crossed like this. One is in one direction, the other one is perpendicular to it. So that if I put the two together like this, no light comes out. All the light is blocked. Now if I put a model such as this, birefringent material, inside of that, you still don't see anything because the model isn't stressed. But if I stress the model, you see lines appearing. And where you see a discontinuity in the material, you see these lines very close to one another. The closer they are to one another, the higher the stress. And for a point such as this point here where you see black, or all of this black area here, all that means is that there is no stress at those points. It's like the neutral axis in bending. So doing this will, and of course counting these lines called fringe lines, will allow you to be able to get a whole field view of stresses. You can turn that back on, thank you. To get a whole field view of the stresses, number one, and number two, be able to analytically calculate the stress value and the direction of the principal stresses and all of that. It is, in fact, one of our students, who I think is graduating in the spring, is just on a senior project on this, which will be presented in the project symposium. So if you're interested, I suggest that you go and see that. That'd be sometime in late May, this project symposium. So I just wanted to show you this so that you get an idea of stress concentration and how these lines are very close to one another where you have a discontinuity, and the fact that you can actually measure all of that. Now, insofar as what we were talking about last time, I think I just may have started talking about the maximum distortion energy theory. Is that correct? Okay, good. Then we'll continue with that. Excuse me. So, to refresh your memory, maximum distortion energy is an offshoot of another theory of failure called maximum energy, maximum strain energy theory of failure, which says that whenever, at any point, the strain energy density, I talked about that, right? Strain energy per unit volume. This equation. That's strain energy in the material. Whenever the strain energy in the material at the location of high stress, maximum strain energy density in the material, reaches that at yield in a simple tension test, the material will have failed. This is the total strain energy in the material. The strain energy that we are interested in is that part that produces distortion, meaning change of angle, change of shape, not change of size, but change of shape. I don't recall whether I gave you this example or not, but it's very quick to do that. If you have a hydrostatic state of stress, at a point where all stresses are equal, say that little cube you take down to the bottom of the ocean, still a cube. Smaller cube, but it's still a cube. No shape change, just volume change. And we also know that yielding, which is the type of failure that occurs in ductile materials, is the result of shape change or angle change or shear stress, and not volume change. In fact, if I draw Mohr's circle for this, oops. That's all I get. 3 more circles. degenerate it down to a point. There is no shear stress. Shear stress is 0. And if there is no shear stress, there will be no yielding. Therefore, we should not take into account all of this stress, but only that part that produces distortion. So, taking a look now at what's on the screen. General state of stress at a point with the principal stresses shown. We say we can divide this into two parts. One part where all of the stresses are equal, similar to what I have shown you here, results only in volume change, no shape change. The other part, which is the leftover of the initial stress state, causes all of the distortion or shape change. Therefore, what I should be considering is the strain energy density due to that, not that. Therefore, we must come up with a way to measure this or find this strain energy density. Now, as you look at this, a question should come to your mind that although it is true that since these three stresses are equal, this part produces no shape change, only volume change. That's true. But why are these all equal to sigma average? Why not all of them equal to sigma 1 or sigma 2 or sigma 3, and then we get the leftover, whatever that is. Unfortunately, your book doesn't tell you why that is the case. So I'm going to put a few things on the board whereby through a homework problem that I will assign to you afterwards, you can actually prove that this is the only way it should be. Any other way will not separate the strain energy due to volume change from the strain energy due to shape change. Okay? So let me do this. In order to find the total strain energy under the general state of stress, such as what you see there, we add together the strain energy produced by sigma 1, sigma 2, and sigma 3, all of them. Therefore, U will be equal to sigma 1, epsilon 1 over 2, plus sigma 2, epsilon 2 over 2, plus sigma 3, epsilon 3 over 2. That's through the principle of superposition. For each of these now, I substitute the values for the strains. And remember that epsilon 1 is not just equal to sigma 1 over E, but it is sigma 1 over E minus nu over E times sigma 2 plus sigma 3. And similarly, epsilon 2 and epsilon 3. And you should be able to write those off of sigma 1. To get our strain energy as a function of stresses only, with no strains in it, we substitute for these strains from this equation. Epsilon 1 here, epsilon 2 there, epsilon 3 there. And then we get this. We get U equals 1 over 2E times sigma 1 squared plus sigma 2 squared plus sigma 3 squared minus 2 nu times sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 1 sigma 3. Now everything is in terms of the stresses. Now, let me go ahead and put sigma average here, and then I'll show you why that should be sigma average. If I want to find the strain energy due to this, I need to subtract the strain energy due to that from strain energy due to the original state of stress. This is strain energy due to the original state of stress. I want to find this and subtract it from that. So U average equals what? How do I find U average? Average this is a general state of stress strain energy. If instead of this I have that, will I not substitute sigma average, sigma average, sigma average for sigma 1, sigma 2, and sigma 3? And that'll give me the strain energy for that. Then I can subtract it from that. So if I put all of these equal to sigma average, this is what I get. I get 3 sigma average squared divided by 2e times 1 minus 2 nu. And then we subtract strain energy density due to sigma average from the total strain energy. So the distortional strain energy is equal to the total strain energy minus that produced by the average stresses. That will give you the part of the strain energy that is responsible for the distortion or changes of angle or shape of the material. Any questions? So that's what we're going to do. But before I go, and this is going to be a little long and drawn out, before I go there, let me talk about this on the other side, so you know why this has to be sigma average and nothing else. Well, actually, you're going to have to find that. I'm going to assign it as a homework, but here's a way to find that. We say we have divided the strain energy into 2 parts. One, the one that produces solely volume change, no shape change. All stresses are equal, only volume change. 2, the remaining stresses. So if this produces all of the volume change, that must produce all of the shape change. The volume change due to this stress, this state of stress, must be 0, therefore. So we calculate the volume change here and set it equal to 0. Now your book says, well, take my word for it, it's sigma average. We don't know if it's sigma average. We want to prove that it is sigma average. So we say, okay, rather than calling this sigma average, I'm going to call it just sigma, plain old sigma. And say that whatever volume change this produces must equal to 0. Does that make sense to everyone? You're just going to have to answer me yes or no, because otherwise I can't read. I'll read into some of your faces whether or not you understand, but not all. We divide it into 2 parts, volume change and shape change. The one that's due to shape change must produce no volume change. So we calculate the volume change due to this state of stress, set it equal to 0, and solve for sigma. How do we do that? I'll show it to you two-dimensionally first, and then we can deduce the three-dimensional from that. Rather than looking at volume change, let's take a look at this. A unit square, 2 dimensions, not 3 dimensions. If this is under some state of stress, which produces strain in this direction and in that direction, then after change of shape, this will look like this. All of these are 1, the original sides of the triangle. Square. Whatever change of length I have must be equal to the strain, because strain is change of length divided by original length, and the original length is 1. So that's a strain. So I'll call this epsilon 1. Oops, I marked both of them the same, and sorry about that. That's epsilon 2. Let's calculate the change of area. Delta A equals the final area minus the original area. Area after deformation minus area before deformation. That's equal to 1 plus epsilon 1 plus epsilon 2 plus epsilon 1, epsilon 2 minus 1, which is equal to approximately epsilon 1 plus epsilon 2. Because in all of the problems that we consider, the magnitudes of the strains are very, very small. And therefore, the product of strains is much, much smaller than the strains themselves. As an example, for example, what I'm saying is that 100 is negligible as compared to 10,000. Because if this is 100, that's 100, that's 10,000. All I'm saying is that 1 over 100 is much, much larger than 1 over 10,000. Okay? So this is negligible with respect to that. So this is all we get. So if this is delta A for 2 dimensions, what do you think delta V is for 3 dimensions? The change of volume.
Epsilon 1 plus epsilon 2 plus epsilon 3.
That's it. That's right. It just follows. Or you can do this 3-dimensionally if you like. You get epsilon 1, epsilon 2, epsilon 3, 3 of these, and one term epsilon 1 times epsilon 2 times epsilon 3. All 3 of them multiplied by one another. So this is approximately equal to epsilon 1 plus epsilon 2 plus epsilon 3. So this is the change of volume. This is my state of stress, my sigmas. For each of these, I find epsilon 1, epsilon 2, and epsilon 3 for that state of stress. And add them up, and I say that change of volume must be equal to 0. Once I do that, then I can solve for sigma 1, for sigma in terms of sigma 1, sigma 2, and sigma 3. Does everybody follow that? What we do is use this equation except that this is sigma 1 minus sigma, that's sigma 2 minus sigma, that's sigma 3 minus sigma. Put them into there, find epsilon 1, find epsilon 2, find epsilon 3, add them up, set them equal to 0, and prove that sigma must be equal to sigma 1 plus sigma 2 plus sigma 3 over 3. So that you do as a homework problem. So now we have found the strain energy density for distortion by subtracting that due to volume change from the total strain energy. We can calculate the strain energy due to density, due to strain energy density due to shape change, and it will come out to be like this. So I'll just simply subtract this from that and substitute for sigma average, sigma 1 plus sigma 2 plus sigma 3 divided by 3, meaning of average. Okay? If I do that, this is what I get. Distortion energy is equal to 1 plus nu over 3 E times sigma 1 minus sigma 2 squared plus sigma 2 minus sigma 3 squared plus sigma 1 minus sigma 3 squared divided by 2 to the 1/2. Oh no, no to the 1/2. I'm one step ahead of myself. That's the distortion energy. Any questions so far? This is the strain energy due to distortion only, that which causes yielding. The theory says this, that failure will occur whenever this equals the distortion energy density at yield in a simple tension test. Let's say you have a simple tension test and you want to find, here's your simple tension test, and we'll just call this stress rather than sigma, we'll call it sigma prime. We'll see why. This is nomenclature that's generally used. If I want to find the strain energy due to sigma prime, only due to distortion, how can I do that? This is strain energy due to distortion for that general case. I want it for that case. How can I do that? What are the stresses in this case? Sigma prime and 0 and 0, right? The three principal stresses are sigma prime, 0, and 0. So all I need to do is just substitute sigma prime, let's say for sigma 1, 0 for sigma 2 and sigma 3, and UD simple tension will be equal to 1 plus nu over 3e times sigma prime squared. So we say yielding will occur when this equals this, when sigma prime is equal to Sy at yield. So we say at yield, sigma prime equals Sy, right? Simple tension test at yield. So for each state of stress, all we have to do is calculate this sigma prime and compare it with the yield strength of the material. Sigma prime can be found, of course, by just comparing those two equations. The two must be equal. Therefore, sigma prime is equal to sigma 1 minus sigma 2 squared plus sigma 1 minus sigma 3 squared plus sigma 2 minus sigma 3 squared over 2 to the 1/2. Agreed? I'm comparing this to that. These two are the same, therefore that must equal to this. Or sigma prime must equal this. This sigma prime is called von Mises stress. But a word of caution on this stress. The name stress is actually a misnomer. This really is not a stress. It doesn't act anywhere in the material. Not at the critical point, not at the highest point, not at the lowest point. It just doesn't act anywhere on the material. It is a gimmick, and a very, very good one, by which we turn a complicated state of stress into one where we only have to worry about one stress, as though this were an axial loading. If that stress exceeds yield strength of the material will have yielded. If it doesn't, there will be a factor of safety. Any questions? Everybody okay with this? Okay, that's it. This is the distortion energy theory of failure for ductile materials. Also notice that this too, although you don't see any shear stresses in that equation, it actually is representing shear stresses. Each one of these included in these three parentheses is 2 times the maximum shear stress from the 3 more circles, right? Sigma 1 minus sigma 2 divided by 2 sigma 2 and all of that. And also notice that if all 3 stresses are equal, there will be no distortion. U will be 0. U distortion will be 0. This will be 0. Sigma prime, which says that this will never yield, because sigma prime will never reach Sy if it's 0. And it's always 0 if the 3 principal stresses are equal. If you have a 2-dimensional case, then the equation for von Mises stress becomes this. If we only have a 2-dimensional case where we have sigma A and sigma B. The third principal stress is 0. And it could be anything. It could be the highest, the lowest, somewhere in the middle. If that's the case, and of course you can prove that by looking at that equation. This is the equation for von Mises stress. Two dimensions. Also, you can write this rather than in terms of principal stresses, which these are, you can write it in terms of general stresses, sigma x, sigma y, tau xy, tau xz, so on and so forth. Those equations are in your book, so I'm not going to write them here on the board. You can consult the book, and they're over there. But one case that occurs very often, generally in shafts, the one that you just had a quiz on, is a case of a stress element in which there is only one normal stress and one shear stress. So this case. In this case, And again, you can prove this by putting it into the equations that we have. Sigma prime is equal to the square root of sigma squared plus 3 tau squared. These are special cases. That's the general equation. That was always good. These are good whenever you have a two-dimensional state of stress and one in which there's only one normal stress and one shear stress. Any questions? What is this the equation of? If these were x, y, z, for example, it looked like this. C a constant. What is that equation of? Actually, an ellipsoid, three-dimensional. Two-dimensionally, if I just write it two dimensions, it'll be that. It'll be this. That's the equation of an ellipse. Partially rotated. And looks like this. That's the solid line is the maximum energy of distortion theory of failure. The dashed line is the maximum shear stress that we looked at last time. Notice that the maximum distortion energy allows you a little bit more leeway here. It says these are safe regions, whereas the maximum shear stress theory does not accept that. So the maximum shear stress theory is more conservative and easier to use as well, used in design. The von Mises, or maximum energy of distortion, is the more accurate of the two, as you will see when I show you the experimental points and how they fall, and generally used in analysis. For example, something fails and you want to know why it failed. You have to have some more accurate numbers, not approximate numbers. Any questions? Okay, let's take a break. Good. Let me show you some slides on the use of this. So here are some load lines that you see. This one, for example, is a load line in which sigma A and sigma B are both positive and equal in magnitude, 45-degree line. The point plots here, that's your stresses, the two principal stresses, sigma A and sigma B. Here's the slope of that line. So you say the factor of safety is the distance from here to where it crosses the failure line, divided by from here to here. Or SY divided by the larger of the two principal stresses, which is what we've used. In that part, in that point, it's exactly the same as the maximum normal stress theory. They all fall on top of one another. Maximum normal, maximum shear, and von Mises, they all have that point in common. But any other point, for example, for this loading, your point plots here, maximum shear stress says your factor of safety is that distance divided by this distance, where you cross over here, or SY divided by that. That's good. But the maximum, about the von Mises says, no, it's from here to here divided by that distance. Is everybody following what I'm talking about? This is what we said before, that you plot that point and allow the stresses to increase until they cross the failure line. The two are a little bit different from one another. However, the experimental points that we get from tests agree much more readily with the von Mises theory of failure, or maximum distortion energy, than they do with the maximum shear stress, especially in this part. They are very much in tune with the maximum distortion energy. So these are the two failure theories that we use for ductile materials. Not the maximum normal, but the maximum shear and the von Mises. Insofar as brittle materials are concerned, there's a little bit of difference between failure of ductile materials, well, actually not a little lot of difference between failure of ductile materials and that of brittle materials. So how does a brittle material fail? Rupture. In other words, by fracturing. It is all done by initiation and propagation of cracks within the material. These cracks are created from minute flaws that may exist in the material, and if those flaws fall at points of high tensile stress, then the flaws will turn into cracks and the cracks will propagate and the material will fail. So this type of failure is very much different than yielding, where we actually have no fracture, but we have plastic deformation, way before, of course, the material may fracture. So other theories of failure are required for brittle materials. And one of them we've actually looked at, we looked at last time without saying as much. But this is called the Coulomb-Mohr failure theory, or internal friction failure theory. It is based on three tests. This is the Mohr circle for the test of a brittle material in tension. And this is drawn exactly as the material is about to fail. That's equal to the tensile strength. Does everybody follow that Mohr circle? A single, one-dimensional stress. You only have one normal stress, no shear stress. So your Mohr circle, maybe I'll draw it over here. So this is what you have. And if this is a brittle material and sigma reaches the tensile strength, the material will have failed. At that instant, Mohr circle is ST and 0, 0 and 0. You get that Mohr circle. You run another test. Compression test. At the instant when it is equal to the compressive strength of the material will fail. At that instant, if you draw Mohr circle, it'll look like that. This is ST. This is SC, that's sigma A, sigma B, the principal stresses. Sorry, not the principal stresses. Normal and shearing stress. Notice that the magnitude of SC is larger than that of ST. Brittle materials are much stronger in compression than they are in tension. For failure, we need crack propagation. Propagation of a crack requires tensile strength, tensile stress, not compressive. So they last a little bit longer, and in fact, although they do fail again by crack propagation, but in compression, that crack propagation is due to shear stresses. There are such things called shear cracks that actually propagate by shear stresses rather than tensile stresses. And if you've worked in the industry anywhere, and if you've seen concrete, for example, tested in compression, you see that it essentially shatters along 45-degree lines, direction of the maximum shear stress. All brittle materials do that. Okay, so we got these two. Then you run a shear test, a pure shear test. Torsion. So that if you have an element there, the stresses look like that. We say that failure occurs here when it reaches the shear strength of the material. And if you draw a Mohr circle for this state of stress, you get something that looks like this. Actually, I should do a little bit better job on this third one. Yeah, that's a little bit better, not much. So this is the shear test. And if we now draw a curve such that it is tangent to all three of these, similar to curve A, B, C, D, E shown on the screen, that curve is the limiting value of any Mohr circle of this material tested in any way. So if we have a Mohr circle for a material that, for example, that looks like this, let's say for some test we get this Mohr circle. Obviously it is not failed yet. We increase the load. That Mohr circle gets larger and larger and larger until it touches this failure line. Then we say that part has failed. This is the internal friction theory of failure. To make the theory a little bit friendlier to work with, we say, let us just estimate that curve with a straight line. And if that's the case, then I only need to have it be tangent to two of those circles, not three. Because it may not be, you may not be able to draw that line to three circles. You won't, in fact. So we only go with the tensile test and the compressive test. And we get this. This is now your failure line, tensile test, compressive test, our Mohr circle, which is now just about to produce failure. It's tangent to those lines. If you set up equations via similarity of these triangles OB1C1, OB2C2, and OB3C3, you will come up with an equation that will look like the equation of the Mohr diagram that we this time called Coulomb-Mohr, that we talked about last time. In other words, if you do that, this is what you get. I'll write that equation on the board for you. You get sigma A over ST. This derivation is in your book, so I suggest that you read it and make sure that you understand it. Minus sigma B over SC equals 1. When we look at this, I say, well, rather than drawing this in a sigma tau set of coordinate system, let's draw it in this coordinate system. And this specifically refers to the case in which one of your principal stresses is positive, the other principal stress is negative. They don't have to be equal. There's just one needs to be positive and the other one negative. Like, for example, in shafts. If I plot this, remember this is sigma A, and that's sigma B. If I plot this, first let's assume sigma B is 0, sigma A equals ST. Sigma A is 0, sigma B equals minus SC. That must be the line then. Connect the 2 points. The equation represents that line in the fourth quadrant. In the first quadrant, both stresses are tensile. Maybe one is larger than the other. Your point plots here. Clearly, whichever of the two is larger governs the design. And this is ST, that's ST. The larger of the two tensile stresses will lead to failure. So the failure theory in the first quadrant is exactly the same as the maximum normal stress failure theory in the first quadrant. Does everybody follow this? Here we have two tensile stresses. There's no compressive stress. Two tensile. The larger of the two governs the failure. Wherever that reaches ST, you're done. So if it's here, if it is like this, that would be sigma A. If your point is here, then the critical stress will be sigma B. Agreed? Because sigma B is larger than sigma A. So that leads to failure. The other two quadrants are very similar. This is the third quadrant. That's the second quadrant. And that would be the locus of all of the safe points that you can plot on that sigma A, sigma B coordinate system. If you take a look at this picture, that's exactly the same as what I have on the board. Safe region, and the two locations where this no longer agrees with the maximum normal stress theory of failure. Now, a couple of things here. First, how do I apply a factor of safety to this? This equation defines failure, right? This defines this line. And if my sigma A and sigma B satisfy this equation, that means they're on that line somewhere. My point is on this line, and that means failure. I don't want failure. I want to have a factor of safety of 2, for example. How do I incorporate that factor of safety in that equation? Or in the graph, for that matter. It doesn't matter, either one. Okay, we go back to 218. Simple linear stress. The material has a strength Sy. I would like to have a factor of safety of 2. What's the maximum value of sigma? Sy over 2. It's very simple. You find this by saying, well, if you need a factor of safety of 2, you shouldn't go all the way to Sy. You should go to half of Sy. In other words, you divide Sy by 2. Or you can say this. You can say, if you want to have a factor of safety of 2, with the strength of material like that, then multiply your stress by 2. And then solve for sigma. Of course, both of them will give you the same answer. Everybody follows that, right? So that's how we incorporate factors of safety. Either divide the strength by 2 or multiply the stress by 2 in this case. If the factor of safety is a general n, then n takes the place of 2. So in this case, if I want a factor of safety of 2, I multiply these by 2. If I want a factor of safety of n, multiply them by n. Or divide these by n. Doesn't matter. They're both the same. In reality, actually, a better way to write it then would be like this. Sigma A over St minus sigma B over Sc equals 1 over n. Graphically, what we have done is this. We have said, this is not our limiting value. That's our limiting value. Our load line is going to cross that green line before it gets to the purple line. Factor of safety of n, whatever that ratio is. Okay? Any questions? So that's one point. Another point. And this, of course, you can do with any failure theory. Another point. If we have this situation, then a stress element here will be in pure shear, like that. Agreed? That's in pure torsion. If I want to find the principal stresses so that I can plot my point here, then I'll draw a Mohr circle for that. Here's one point. There's the other point. This is tau. That's tau. That's my Mohr circle. I'm going to change that line so that it will go through the center here. Right? The two non-zero principal stresses are equal to tau in magnitude. One of them is tension, of course, the other one is compression. Meaning that at this very point, I can represent the stresses like this, or as you can see, that's 90 degrees, transforms into 45 degrees here. So I'll get this. Correct? Those are my principal stresses, this one and sigma. Actually, sigma A and sigma B, that's what I've called them. Now, if this is a brittle material, and this is the state of stress, then failure should occur when this reaches the tensile strength of the material, the tension one. not the compression one. Compression material is stronger. When this reaches the tensile strength of the material. Well, let's see if this gives us the same thing. Erase that green line now. And here's my point. I just draw a point where the two stresses are equal in magnitude. There it is, right there. There is my load line. There's my strength line, and they cross over here. So this says, as soon as this sigma A reaches this value, failure occurs, right? But that's not what it should say. It should say when it reaches that value, tensile strength of the material. In other words, here. Everybody following? If you have any questions, you better ask now, because this is going to come up and you're going to have to use it. If something doesn't make sense, please let me know. So, as we look at this Coulomb-Mohr theory of failure, we see, well, this is not a correct answer. That's the correct answer. So this needs to be modified. And, and this is true for all values of sigma A, magnitude greater than sigma B, sigma A positive, sigma B negative. They all should give you this ST. And they don't, according to this theory. So we'll modify the theory and use, rather than just one line, we use two lines. One, one is this. The other one is that. Okay? In all cases, regardless of the type of failure theory that you're using, you have to consider two things: strength, stress. Load line, strength line. Wherever they cross, that's failure. Factor of safety would be the ratio that you have left before you get to a point where they cross. The equation for this line is just ST over sigma A. For that one is a little bit longer and drawn out. It's in your book, so I won't rewrite it on the board. And I'm not a great fan of equations in general. You should actually understand what you're doing rather than plugging numbers into equations. But let me just show you, they have an equation in the book where they find the factor of safety not for the modified Mohr, but for the Coulomb-Mohr, for this one. And just show you quickly how that's done. So the equation of the strength line is the one I have over there. I'll rewrite it here. That's the equation of this line. How do we know? Let's say sigma B is 0, sigma A equals ST. Sigma A is 0, sigma B equals minus SC. That's a straight line. You connect it, and you got the equation of the failure line. You can also write an equation for the load line. just write the equation of two straight lines. We say failure will occur when these two cross. So if I substitute sigma b over here and solve for sigma a, I should get this value here, should I not? Two straight lines, you solve their equations, you get coordinates of the point of intersection. So I'll call that sigma a critical. And this, of course, will be sigma b critical. Factor of safety, sigma a critical divided by sigma a, or sigma b critical divided by sigma b. Either one. Or the length of this line divided by the length of that line, however you want to see it. All of those are exactly the same. If you do that and you solve for the factor of safety, you get this equation. Oh, actually, we have the equation right here. Right here. You get that equation if you do that. If you do it for the, we also have the part over here and over here in the modified Mohr line. This was for the Coulomb-Mohr. For the modified Mohr, this is just St over sigma a. And this one, you do exactly the same thing. You solve this equation, write the equation of the load line, put them together, and come up with the factor of safety. And that will give you this equation, which is a little bit more long and drawn out than the other one. Let's see, which one of these do I want to give you? This one or that one? Yeah, this one. These are written in different forms, so this is just one form. If you see a different form in the book, do not be surprised. This is not for this, but for modified Mohr, for this one. This is Coulomb-Mohr, what I'm about to write. Modified Mohr. N equals SUC SUT divided by SUC sigma A minus SUT times sigma A plus sigma B. Again, there are different forms of writing that equation, but that's your factor of safety with that. But you should be able to do what I just did here. Write the equation of the load line, write the equation of the strength line, solve them together, find the critical values, and use them to find the factor of safety, rather than just simply plugging numbers into equations. Because somewhere along the line, I will ask you to do that, either with this failure theory or with some other failure theories. They're all exactly the same. They all include a load line and a strength line. The strength line will represent various types of failure. One, ductile failure, brittle failure, and so on. Any questions? Okay, let's see. I think we've covered all of this. Yeah, here, this I want to show you. Those are experimental points. And as you can see, they agree much, much more with the modified Mohr than they do with the Coulomb-Mohr. That's why we should use the modified Mohr. the Coulomb-Mohr is a little bit too conservative. And this is that same one for a load of sigma A, sigma B, and all of that. So, okay. Any questions before I do a couple of example problems? Okay, let's do this one. This is in your handout. It says the 150 kilogram sign is supported by pipe OD 125 millimeters, ID 100 millimeters, which is fixed to the pavement as shown. The force P equal to 2 kilonewtons is due to wind and is assumed to act at the mass center of the sign. The pipe material is a ductile steel with a yield strength of 250 MPa. What is the factor of safety against yielding? So the first thing you need to do in cases such as this is identify the critical point. Where is the critical point in this body? The stresses at the critical point then need to be found, and a theory of failure used to find the factor of safety. So from here on out, whenever you're asked to find the factor of safety, you must indicate what failure theory you're using. And very seldom will you be right if you just say Sy over sigma, as you have seen. So you have to identify your failure theories. Since this says yielding, what is the factor of safety against yielding? Then you must be using a ductile failure theory, because ductile materials fail, brittle materials fracture. We identify this section, right, at the base as the most critical section because the moment is maximum there. There are three components of the moment applied to that section. One is torsional, the other two are bending moments. We calculate each of these by considering the moment created by these two forces about that base. Now you can do an R cross F and find all three of them at the same time, or do them one by one. It doesn't matter, whichever you like. The moment about the x-axis is P times that distance, 1.2. The moment about the z-axis comes from P again, but this time multiplied by this moment arm, 3 meters, 6 kilonewton meters. And finally, moment about the y-axis, which comes from the weight, W, and that's equal to 1.2 times W down in here. The section at the base then looks like this. It's under a compressive load, which is essentially the weight of the sign, 150 kilograms, multiplied by 9.81, of course. Then the shear force P, which is this force, transmitted down in here, and the three components of moment that we just found. In order to find where the maximum normal stress acts, you must combine the two bending moments, My and Mz. You must combine them. It is not whichever is larger. They are both acting at the same section. This is the same thing as something that I think I talked about last time, and you've had in 219. Let me show you quickly. There's a bearing here, and there's a bearing there. And you have forces like that in two different directions. So one of them gives you a bending moment, for example, in this direction, in the horizontal plane. The other one gives you a bending moment in the vertical plane. The maximum moment is the sum of those two. And by sum, I don't mean adding their magnitudes, but adding them vectorially. Moments are vectors. So to find the maximum bending moment, and here, although I haven't done it, you should actually identify the point of maximum tensile stress. And I'll let you do that as some sort of a homework problem. Now, combine these two vectorially, like that. Square root of sum of the square, 6.25 newtons. There's the area, cross-sectional area, and moment of inertia, I. So you have, at the end, you have a moment and a torque. You use those to find the stresses. And of course, you should add to those stresses, to the normal stress, that is, P over A. Because we have a compressive load P, and somewhere along the line, the normal stresses are compressive, so they add. So it looks like this. From the tensile, from the moments, you get this. From the applied load, you get this, all compression. Therefore, insofar as magnitude is concerned, the maximum stress occurs where those two add. They're both compressive. And since you're looking for yielding, tensile and compressive stresses really don't make any difference, because slip takes place whether your force goes in one direction or the other direction. Whether the applied force is tensile or compressive doesn't matter. So, sigma mc over I plus P over A, you have all of the values, substitute in here, 555.2. Tau, Tc over J, 10.6. So you are now looking at the most critical point and this state of stress. Agreed? One shear stress, one normal stress. To use the maximum shear stress theory, what we do is find the maximum shear stress. And it will be this. If this is what I have, my Mohr circle looks like this. Sigma, tau. Actually, I've shown it as negative, so let me plot it as negative. And then 0 and tau. There's Mohr circle. And there's your maximum shear stress. And of course, the maximum shear stress is the square of half of the normal stress plus the square of the shear stress, gives you 29.6. That's the radius of Mohr circle. And that is the largest Mohr circle, by the way, because the middle principal stress is 0. That is the largest Mohr circle. Therefore, maximum shear stress theory of failure says failure will occur when this reaches the maximum shear stress at yield in a simple tension test. The yield strength of the material is 250. At yield, the maximum shear stress is 250 over 2. Divide that by tau max, you get 4.2. To use the maximum distortion energy, we find the von Mises stress. For this special case is sigma squared plus 3 tau squared, 58.2. We divide the yield strength by that, we get 4.3. Notice that the two are very close to one another, but the factor of safety from von Mises is a little bit larger than that due to maximum shear stress, because maximum shear stress is more conservative. Okay? Any questions? One more before we call it a day. This one is in your book. I won't solve the example problems in the book, but I sometimes solve example problems from the book. Problem 516. This is an ASI 4142 steel quenching tempered at 800 degrees Fahrenheit, has SYT 245, SYC 285. This is actually good because it's similar to brittle material failure theory anyway. 235, SYC 285. And epsilon f equal to 0.07. Your book says if it's greater than, epsilon f is, by the way, failure strain for the material. In other words, when it fails, actually breaks, what's the strain? That's what we call epsilon f failure. For the given state of plane stress, determine the factor of safety, B, plot the failure locus and load line, and estimate the factor of safety by graphical measurements. Specifically, given state of stress for problem 516 says sigma x is 125 and tau xy is minus 75. Sometimes you're given these outright, sometimes you have to find them, such as the example problem we just did. So here is your element. I mentioned that I will talk about nomenclature for signs of stresses that are universal and used not just for Mohr circle, but anyway, which are different from those of Mohr circle, but I haven't talked about it today, but I'll talk about it next time. That's how I have drawn this 75 in the direction that I have drawn, which is not good. You may be wondering why I didn't point it upwards. It's because of the minus sign, and I'll talk about that next time. So, this is the state of stress. Very similar to this problem. We find the principal stresses. Oops. Better not go through both of those points like that. Sigma A, sigma B. Leave it up to you to say that sigma A is equal to 160 and sigma B negative 35. It is always this way when you have one normal and one shear stress. One principal stress will be positive, one principal stress will be negative, the middle principal stress is 0. Always. Okay, then we do the Mohr theory for ductile materials. In other words, this 235 285 modified Mohr, Coulomb-Mohr. That's material strength. Now our load line, sigma A is 160, and sigma B is minus 35. So my point plots here. Agreed? This is 160, and that's 35, negative 35. My load line is composed of a straight line from the origin through that point, continued until it crosses the failure lines, whichever failure theory you want to use. I think I have, well, I've done both. If you're using modified Mohr, factor of safety is 235 over 160, right? For modified Mohr, this is your failure point. That one is simple. Anybody follow? This is modified Mohr, never mind the dashed line. There's your failure point. Factor of safety, that divided by that. Comes out to be equal to, well, actually I haven't calculated for that one. No, I haven't calculated for that one. Let's use the Coulomb-Mohr. We write the equation of the Coulomb-Mohr line, sigma A over 135 minus sigma B over, sorry, not 135, 235, minus sigma B over 285 equals 1. Load line is the equation of this green line. So sigma A equals negative 35 over 160 sigma B. Oh, the other way around. Sigma B equals that sigma A. There. I substitute sigma B from here to here and solve for sigma A. And when I do that, I will get this value here. I'll call it SA. So sub for sigma B, call sigma B SA, sorry, sigma A SA, and find SA is equal to 199.1. Then your factor of safety is 199.1 divided by, that's SA. This is 199.1 KSI. Divided by 160. Comes out to be 1.2, 1.24. So that's the factor of safety for that. This is the method which you should employ because it helps you understand the material rather than just plugging numbers into equations. You can, of course, then use this equation, this very same equation, put an n here, put sigma n, sigma b, solve for n, and make sure that's equal to that. That'll give you the same answer. But you should be able to do both of those, writing equations for lines and solving them together. Any questions? Okay, I'll see you next week. Have a good weekend.